Right, we can start. So, hi everyone. Today we are excited to have Dr. Adam Michael here. Adam is a postdoctoral researcher at the Johns Hopkins University of Applied Physics Laboratory. He combines global MHD and native simulations to study the process of governing energetic particles and their feedback on global geospace systems. His research interests includes transport and acceleration in the magnetic tail and the dynamics of the ring current and radiation belts. He's a group lead in the magnetic tail plasma sheet and inner magnetosphere at the center of geospace storms. And today, Adam will talk about cross-scale modeling of storm time radiation belt variability. So you have about 45 minutes to talk, and it's yours.
Great. Well, thank you so much to Jose and Amy for inviting me to give this seminar. I'm really excited to present this work today that we've done as part of the Center for Geospace Storms, working to develop a storm time model of the radiation belts. And I've had a tremendous amount of help from all of my collaborators that you see here on the bottom screen. They've been instrumental in every phase of this work. So I'd like to give them a big round of thanks for all that they've done in this development. Yeah, here we go. Before jumping in, I just wanted to give a quick outline of my talk so you'll know roughly where I am as I progress through it. I will give just a very brief overview of radiation belt dynamics, highlighting some of the key processes that are governing the variability and highlighting some of the influence that the cold plasma density and intermagnetosphere has on regulating those processes and why it's important to capture that. I'll then go into describing the global geospace and radiation belt model that we're using. I'll briefly describe the model components that comprise the kind of global radiation belt model, and also discuss implementation of pitch angle scattering and acceleration that we've developed as part of this work. And then finally, I'll run it out and show some results from the 2013 St. Patrick's Day storm, which is a case study that that's been well studied, and we've applied this radiation belt model to study how the varying background plasma conditions affect the radiation belt themselves. So the Earth's radiation belt is comprised of very energetic electrons that are trapped in Earth's magnetic field very close to the Earth itself. And the radiation belts themselves are extremely dynamic, and this is especially true during geomagnetic storms. And you can see that in the video on the upper right-hand side, which is actually Van Allen probes data of 4.5 MeV electrons during September 2nd, 2012 storm. And during these geomagnetic storms, the radiation belt intensities can vary up to orders of magnitude on timescales from minutes up to days themselves. And this dynamic variability is controlled by shifting balance by competing acceleration loss mechanisms that act over a wide range of spatial and temporal scales. And this has been really nicely put together in an image that you see on the left-hand side on the Van Allen probe's gateway, where they've highlighted a lot of the different acceleration and loss processes that are occurring during these events. And I tried to color code them by how each of these processes impact either accelerating and energizing the radiation belts or causing loss from the system. But these processes often act simultaneously in a synergistic manner, so disentangling the relative role of each one is remained a major challenge. It's a huge area of research today. And without getting into too much to all of these processes, I'd like to highlight one in particular, wave-particle interaction, which you can see up on this top of this screen here, which is a really key source of scattering particles into the loss cone and causing them to be lost from the system, and also is really important for energizing particles up to those ultra-relativistic energies. So understanding and capturing wave-particle interaction is just key to understanding and being able to predict the radiation belt intensities during storm time periods. So the way plasma waves and energetic electrons interact is through resonance, and this can be larger timescales, like the drift period, where electrons will resonate with ULF waves causing radial diffusion effects. But this resonance can also be very local. And that can result in the resonance condition, which you see on the lower right-hand side, where the Doppler shifted frequency of the wave matches a resonant harmonic of the relativistic gyro frequency of the electron. And that causes the first adiabatic invariant to be violated, which then scatters and accelerates the electron. And if these electrons are close enough to the loss cone, they can be scattered into the loss cone and precipitate into the atmosphere. And this type of wave-induced precipitation is one of the major energy sources into the ionosphere itself. And for lower energy electrons around 10s or so keV, this can drive the diffuse aurora, which is significantly important to impacting ionospheric conductivity and MI coupling itself. But also for much more energetic electrons of several hundreds of keV or so, this can also alter atmospheric chemistry. And as I mentioned on the previous slide, this is a major source of both loss and acceleration up to any of the energies for these radiation belts. So it's a key, very key physical process itself. There are a whole host of waves that interact with the radiation belt electrons in the intermagnetic medium itself. I've adapted this image from the Arasai team in Japan, where in the middle of the panel, you see the storm time plasmasphere there in light blue and magnetopause up at the top. And each of the panels on the outside show different wave modes that are in the inner magnetosphere and resonate with radiation belt electrons in some form or fashion. And you can notice, although hopefully it's large enough on your Zoom screen, is that each of these wave modes act over very different frequency ranges, which means that they will interact with different energy populations in the radiation belt themselves. So just to highlight a few of them, ECH waves tend to be more in the near plasma sheet, and they resonate with lower energy electrons in tens of keV or so, and potentially are important for the diffuse aurora that I mentioned on the previous slide. And the plasmaspheric His resonates and is extremely important for creating the slot region in the radiation belt themselves. And one I want to highlight in particular are Whistler mode chorus waves, which you see here on the middle panel on the right-hand side. These waves are electromagnetic waves that are primarily in the pre-midnight to dawn sector in the inner magnetosphere. And these are critically important for both scattering electrons into the loss cone, but also accelerating them to MeV energies. And they're one of the primary waves that we think are important to creating the MeV radiation belt populations. And the reason why they included the storm time plasmasphere on that previous plot is because the cold plasma density is critically important to the generation of these plasmaspheric waves. So what I'm showing here on the upper right-hand panel is work done by David Malaspina that he published in 2016, where on the left-hand side, shown here in panel D, I took it from his paper, he has the waves plotted as a function of frequency on the y-axis and L shell on the x-axis. And here you can see that while lower band chorus rates have a slightly higher frequency, disentangling magnetosonic and His waves can be a little difficult. But what's shown on the right-hand side here, instead of parameterizing the waves by the L shell, which they're observed, he now has reparameterized it by distance from the plasma pod. So that black dash curve occurs at 0, that's the local plasma pod's location. And you see that this plasmaspheric density strongly separates the His waves, which are inside the plasmasphere, and the lower band cores, which are predominantly outside the plasmasphere themselves. And this cold plasma density is not just does not just affect the rotation and generation of the waves, but it also significantly impacts the actual resonant interaction that these waves have with the electrons themselves. So what I'm showing here on the bottom left-hand panel is the minimum resonance energy that electrons need in order to resonate with a wave of frequency omega. And this is proportional to this EC, which is a characteristic cyclotron energy, which is proportional to the electrogyro frequency and plasma frequency. And here you can see that this minimum resonant energy is inversely proportional to the density itself. So for higher plasma densities, such as in the plasmaspheric plume, you'll need a lower minimum resonant energy in order to resonate with those waves. So higher positive density allow for lower energy electrons to resonate, while much lower density regions allow a much higher energy electrons to resonate themselves. And that is crucially important because the plasmasphere itself is extremely dynamic during storm time periods, with the extension of the plume to the day side, as it co-rotates in the dusk region, seen on the bottom right-hand panel there. Common computational techniques that we've used to study wave-part interactions is the community has commonly treated wave-part interactions as a diffusive process, where resonance with ULF waves provides radial diffusion inwards into the magnetosphere, energizing the particles as they move to larger magnetic fields. And additionally, the local scattering and resonance on the order of a gyro radius can also be modeled through quasi-linear theory, pitch angle scattering with Whistler waves that way. This is commonly used by Fokker-Planck diffusion models, which can capture the radial, pitch angle, and energy diffusion through the use of quasi-linear diffusion coefficients. These models have been extremely successful in combining the combined effects of resonance with multiple wave modes simultaneously, and have been able to be applied to study the long-term variation of the radiation belts over the entire lifetime of the Van Allen probes mission themselves. So they've been incredibly powerful tools for us to study the system. However, these models are bounce and drift averages and don't capture a non-diffusive process that can be really important during very active periods. So during storms, some processes, such as the one shown on the right, where we have magnetic trapping and rapid transport due to these mesoscale flows, shown in the middle panel here by Sasha Yukorski's work in 2018, as well as very dynamic magnetopause loss, where these electrons are trapped up in Kelvin-Helmholtz vortices on the dust side flank, causing additional loss of the radiation belts in those regions. And that was work published by Karim Sarathia in 2017. So on these much shorter timescales, what we know during storms where we have these non-diffusive effects that can cause rapid variability on the order of minutes to hours, these Fokker-Planck diffusion models have a little bit more difficulty trying to capture those variabilities. Other techniques that people have used to try and capture some of these non-diffusive effects are global magnetosphere and test particle simulations. And these models evolve electron test particles through the 3D electromagnetic fields provided by a global magnetosphere simulation, such as Gamera, which you're seeing on the upper left-hand corner, and upper right-hand corner, and LFM, which are two common models that have been used. These models solve either the guiding center trajectories for electrons or full orbit trajectories, the potential some other ion studies here. And they treat the radiation belts as pure test particles, so they're not providing any feedback in the global magnetosphere. But these have been extremely powerful tools to study effects such as magnetosonic waves driven by CMEs accelerating the radiation belts to relative scalarities. They can also capture drift orbit bifurcations during storm time periods, mesoscale injections, which we saw on the previous slide, as well as ULF wave transport. Those are also really important for acceleration from radial transport themselves. I will note that these models are more computationally expensive, so they can't model the long time periods that the Fokker-Planck diffusion codes can, but they are very powerful for dynamic periods such as storm time. And just to kind of show some of that work here, this is a previous work that Karim Sarathia published in 2018, where he modeled this same 2013 St. Patrick's Day storm with this global NHDN test particle simulation based off of the LFM and our test particle model CHIM. And what Karim modeled his event is he first modeled the pre-storm belts and showed that belt was quickly wiped out by the sudden storm commitment and impact of the CME on the system, which caused a rapid decrease of the magnetopause inward, removing a lot of that initial radiation belt population. However, he did include injections from the plasma sheet themselves and was able to capture the rebuilding of the belt throughout the late May phase and early recovery phase of the storm, and showed very good quantitative agreement below 1 MeV for all radiation belt energy electron channels. So what I'm showing here in the bottom left-hand side are those kind of three different stages of the storm. The pre-storm belt before the event itself, which you can see in the bottom panel B in the SIMH and the sudden dropout in main phase injections and initial recovery buildup. What's shown on the right-hand side are these both Van Allen probe A measurements for 500 keV, 1 MeV, 2 MeV, and 3 MeV electron channels, and then synthetic measurements from extracted from the model shown in red. And while the 500 keV shows a very, very good agreement, the higher energies in the late main phase, early recovery phase show several order, at least an order of magnitude decrease in predicted energy from the simulation itself. And it was thought that this discrepancy was due to the lack of wave-particle interactions included into test particle models, which are until recently just unable to capture that physical process within the simulation. So that's one of the main goals that we've been trying to work on in our group, and that we actually have accomplished, and I'll show you how we've done that in our simulation. But our goal here is to create a global radiation bubble model that can both capture the non-diffusive effects that are critical during storm time periods, as well as the diffusive processes such as wave-particle interactions. And first, we do that through evolving our test particles through very accurate storm time electromagnetic fields, which we are provided by through the MAGE geospace model, which is being developed as part of the Center for Geospace Storms. That global magnetosphere model shown here on the top right-hand panel, this is during the exact same 2013 St. Patrick's Day storm period. And the MAGE model also uses has RCM in the inner magnetosphere, which provides very accurate storm time ring current pressure to have as part of its accurate storm time electromagnetic fields. But we also use the RCM to solve for the cold plasma density. Inherently has a zero energy channel bin in RCM. And RCM then evolves the cold plasma self-consistently with the electromagnetic field provided by the global MHD simulation. So that plasma density is then ingested back in the MHD simulation, and we see that evolution of the density back down in the bottom left-hand panel. And then we then use those magnetic fields and densities to evolve test particles through them. And you can see that on the bottom right-hand side with our test particle simulation called CHIN. And this is done in a modular framework so that we can turn the effect of waves on and off and be able to isolate each individual mechanism that can be affecting radiation belt damage to try and disentangle those processes and try and understand which ones dominate and when and where. So to be able to incorporate wave particles into our test particle simulation, we did that by simultaneously evolving the test particles through the MHD generated magnetic field simultaneously with evolving them through what's called more chorus waves provided by an empirical wave model. And we solve the Fokker-Planck diffusion equation simultaneously with the test particle integration for their motion through the electromagnetic fields. And we solve the Fokker-Planck diffusion equation using a stochastic time-forward stochastic differential equation, which you're seeing here in the middle panel. And just like the Fokker-Planck equation, these coefficients A alpha, B alpha alpha are directly dependent on diffusion, quasi-linear diffusion coefficients. These diffusion coefficients, we are taking them for expressions, analytical expressions directly derived by Danny Summers in his 2005 paper, which assumes parallel propagating waves. And since they're analytical expressions, we can solve for these diffusion coefficients for each individual wave particle interaction. So I wanted to briefly walk you through the algorithm we use to solve for these test particle simulations. On the right-hand side just shows a system architecture overview of the actual information being passed back and forth. But as test particles are being evolved through the MHD fields, each individual step we check to see if the particle is in the presence of waves. We then solve the resonance condition, which you see here, that first equation in the middle plot, for the wave to see if it actually is in resonance with the wave and if that frequency is present in the wave model itself. We then can take the magnetic field and density at the particle's location directly from the global magnetosphere simulation and calculate directly the diffusion coefficients, both the alpha and the mixed diffusion coefficient and the energy coefficient for the given test particle energy and pitch angle. Therefore, for each individual resonant interaction and background plasma conditions, we can uniquely calculate the resonant frequency and the diffusion coefficients that drive that interaction itself. And this, therefore, being able to have dependence on the background magnetic field and the density allow our diffusion coefficients to change dynamically with the actual plasma solution and wave model in our simulation. So that was a lot of in-depth talk. I wanted to just go a little bit to describe exactly how we do that in our simulation. And in order for us to be able to resonate with these waves, we need accurate description of the waves in full in 3D space and as a function of time. These Whistler mode porous waves are driven by temperature anisotropies that we do not capture in single fluid NHD. And because the wave amplitudes of porous waves are much smaller than the actual magnetic fields in the magnetosphere, it's okay to assume that the processes generating the waves are independent of the actual global magnetic fields, and we take them separately. But we still need to be able to define them as a function of location in the simulation and geomagnetic activity. So in this simulation, we have used empirical wave models, which are derived from the Van Allen probes measurements over the 2013 to 2019. And those empirical specifications are shown on the upper right-hand corner, provided by Wenli and Jiaoshen Chen at Boston University. And here you can see lower band porous wave amplitude as a function of L shell and MLT in the equatorial plane, so magnetic latitudes below 10 degrees, as a function of geomagnetic activity index. And here we're using the SML star index. And then because the plasma density is really critical to defining where we would expect porous waves to be in a simulation, we reparameterize the empirical wave model to be distance from the plasma pause, as David Malaspina did in his 2016 paper. We are then able to calculate where the plasma pause location is in the actual simulation, and then ingest the porous waves dynamically according to that plasma pause location. So that's what I'm showing here in the bottom video, where you see the plasma density in equatorial plane on the left-hand side. And then shown on the right-hand side is the dynamic variation of the porous wave intensity relative to the plasma pause location, which is shown in some magenta period here. And this allows us to have a dynamically varying porous waves exactly where we would expect them to be in the simulation, given the background cold plasma density. What you're not seeing in the video is the variation of the wave amplitude with SML index in the actual simulation itself. But we are capable of updating those wave amplitudes as a function of SML star, which you can see in the top left-hand panel, which is the SML index taken from Supermag during the 2013 St. Patrick Day storm. So this allows us both to change the wave amplitude as a function of time and location in the simulation, consistently with the background plasma. So to give a description of the actual simulation that we've done, we wanted to isolate the impact that the background varying magnetic field and density has on wave part interaction, resulting acceleration and loss of the radiation belt themselves. And so in order to isolate that effect, we only included the evolution of the pre-existing belt itself. What you're seeing on the right-hand side is a snapshot of our test particle simulation, where we have initialized over 2 million test particles between L shells of 2.5 and 8 RE, and between energies of 50 keV up to 5 MeV. They also had a uniform distribution in pitch angle and magnetic local time. To more accurately make sure that these have a more physical representation of the actual distribution function, we weighted these test particles using 2 outbound RBSP orbits between 10 and 14 UT. And that phase-space density is a function of energy and L shown. I'm showing that in the upper inset on the left-hand panel. And that corresponds to the particle size in the image on the right-hand side, where the weight of the test particle corresponds to the actual number of radiation bound electrons that test particle represents. During this 2013 St. Patrick's Day storm, there was significant chorus wave activity observed between 10 UT up to midnight during the event. We ran two simulations, both parameterized by the exact same initial pre-radiation belt. We ran two simulations during that wave activity region from 10 UT to 14 UT. One simulation did not include any resonance with lower band chorus waves, and the second one did include resonance by lower band chorus waves that I showed on the previous slide. And on top of the wave amplitudes that we get from the empirical wave model, we also have to assume a wave spectrum, which we take here to be a Gaussian profile, and parallel propagation. So there's no oblique propagation of waves in the planned simulation. And I just wanted to further highlight why capturing the density is incredibly important in these dynamic simulations. So what I'm showing here is the local diffusion coefficient as a function of energy on the y-axis and local pitch angle on the x-axis. And as you go from left to right in this image, we're going to higher magnetic latitudes at an L shell of 4.25. And here, just for simplicity, I kept the density constant. So essentially, the magnetic field is increasing from left to right. And you can see that as the magnetic field increases to much higher latitudes, you're shifting the resonance region to much higher energies. And that are several hundred keV and multi MeV particles will resonate much higher on the field line at much larger magnetic field strengths. And this similar effect, although at a much lower rate, is similar if you were to decrease density from left to right while the magnetic field constant. So capturing the variation, both magnetic field and density, is critically important to capturing the effects that wave particle interactions have. And because, and while we're using local diffusion coefficients for each individual resonant interaction, that can be very difficult to try and understand the cumulative effect that these interactions have on the system. So to kind of better capture a snapshot of diffusion, we've calculated bounce average diffusion coefficients at each individual magnetospheric state, where we take a time slice, take the magnetic field and density from that time slice in 3 dimensions, and then integrate the local diffusion coefficients to calculate bounce average diffusion coefficients as a function of energy, equatorial pitch angle, and 2D location. So I'm showing an example of that here in the middle panel here, where this is at an L shell of 4, and I've averaged over the ML2 region. And again, this is the similar plot I was showing in the previous channel, where energy on the y-axis and equatorial pitch angle on the x-axis. And these white regions are regions where there's no resonance. And similarly, if we were just to pick one particular energy and equatorial pitch angle, we can then see what these bounce average diffusion coefficients look like in the equatorial plane. So to go a little bit further into our model, because the cold plasma density and magnetic field variation during storms is very important, that's captured in this ratio of the plasma frequency to the gyro frequency, which is the FP over FC, which is shown in the top right-hand panel. And here I'm showing 4 snapshots during the main phase of the storm throughout the simulation in the upper panel here. And in this region, the cold plasma density varies orders of magnitude from inside the plume to outside the plume. So a lot of the variation that you're seeing in the inner magnetosphere is driven by the evolution of the cold plasma density. Although I will note that the magnetic field is also is non-dipolar itself, and also has variations that is included in this ratio. But here you can see the due to the increased convective electric fields during the storm, the motion of the plasmasphere to the day side, and then as it begins to co-rotate and erode in the upper panel. And what is forming on the dawn side and into the day side as you move into 22 UT here is this lower density depletion region here showing up in blue, which correspond to very low values of this ratio itself. What is seen in the middle panel and the bottom panel are the bounce average diffusion coefficient D alpha alpha for 2 MeV electron with an equatorial pitch angle of 55 degrees. And you can see that as before there's significant erosion of the plasmasphere on the dawn side, that the bounce average diffusion coefficients are largest where the wave amplitudes are largest. So in this midnight to dawn region on the day side, on the dawn side. However, as this lower density region begins to form, that shifts the resonant region to much higher energies. And you can see that the bounce average diffusion coefficients are much larger in this lower density depletion region. And even kind of shifting it much closer to the day side, despite the porous wave amplitudes being largest in the midnight to dawn region here. Similarly, you can look at the bottom panel here, which shows those same exact plots for a 100 keV electron with an equatorial pitch angle of 55 degrees as well. What you can see here is that while we also see a somewhat similar effect to shifting to the downside, this is much less, the 100 keV electrons are much less affected, such that the bounce average diffusion coefficients are predominantly largest where the porous wave amplitudes are largest. And that in both cases, the plasmaspheric plume has shifted the resonance region outside so that neither of these energy electron ranges are resonating in the actual plasmaspheric plume itself. So again, this shows how critically important capturing local resonance and diffusion coefficients are critical to be consistent with the background field, creating this energy dependence in the actual scattering and energization itself. So before those were kind of just looking at the diffusion coefficients without actually looking at the test particles. Here I wanted to show the actual results from radiation intensity from the test particle simulations. And what I'm showing here on each of these panels is the phase space, is the radiation belt intensity averaged in MLT and presented as a function of energy on the y-axis and radius on the x-axis. And what you're seeing on the very far left-hand plot is the initial distribution that we used to weight the test particles. So this is basically the intensity of the radiation belts before any evolution in the system. In the middle panel is the result at the end of the main phase in the simulation where only transport effects are included. So here we don't have any resonance with lower band coarse waves, and we've just evolved the pre-existing belt through the electromagnetic fields provided by the MAGE model. And the first thing you can see is that in regions where the radius is larger than 4, we have a reduction in the intensity relative to the initial distribution. And that's caused most primarily by magnetopause shattering, where a lot of these electrons are lost directly to the magnetopause and therefore reduce the intensity at these L shells. Additionally, if you note, comparing the MeV energies in both transport only and initial distribution, you can see that transport alone cannot cause or does not result in a significant enhancement of MeV particle intensities. And this confirms what Sarathi previously showed in his 2018 paper, and that we see similar intensities before and after the storm of these multi-MeV energies. What you're seeing in the third panel is the result from the simulation when we now do include pitch angle scattering and local acceleration from resonance with lower band chorus waves. And the first striking feature is that at multi-MeV energies, you can see several orders of magnitude increase in the MeV electron intensity. And what's shown on the right-hand side is a ratio of the third panel to the middle panel taken at the end of the main phase of the storm to show the differences between the two. where red shows acceleration of coarse acceleration to these multi-MeV energies. And because we were trying to isolate the effect of lower band coarse waves, we did not include any further injections from the plasma sheet. Therefore, there wasn't any additional source of lower energy electrons that can be further accelerated to MeV energies. So what this resulted in was a reduction in the intensities at energies below 500 keV or so, as these electrons were accelerated up to MeV energies. And you can see that in this blue region here shown in the bottom right-hand panel. But this is an example of how that energy-dependent diffusion that we're looking at the previous slide can efficiently accelerate our test particles to these MeV energies that were observed by the Van Allen probes. To be a little bit more quantitative, what I'm showing are similar plots previously where we've extracted the radiation level intensity from the simulations at 1 MeV, 2 MeV, and 3 MeV at the Van Allen probes A measurement. And this is done throughout the entirety of the main phase of the storm itself. And green shows the results from the coarse acceleration in green, and the transport only model is shown in orange as a reference. So what you can see is that just even in the first few hours of simulation, we can see rapid acceleration of MeV electrons due to wave particle interactions that you can see at the first at 12 UT comparing the green and orange curves. And that as RBSP approaches this first apogee, that we don't see as much acceleration in the 3 MeV energy channel, but there is acceleration in both 1 MeV and 2 MeV. But at the end of the main phase, it's been 14 hours, and it's been sufficient time for all energy channels to show significant enhancement at all L shells of the Van Allen probes measurements. And again, as you note, as we noted on the previous slides, due to the lack of injections in our simulation, we see a decreased intensity at 1 MeV than would normally be expected, and that's as some of those particle populations are being accelerated a little bit further to 2 and 3 MeV throughout the simulation. But again, this just shows the importance of lower band coarse waves in accelerating these particles to these multi-MeV energy channels. So because we also have, because this is a test particle simulation, we also know the location of each test particle as a function of time throughout the simulation. And therefore, we can determine exactly how that particle is lost through the system, whether it's through the magnetopause itself or through precipitation. So here I'm quantifying the losses of the radiation belts as a function of time throughout the storm, both for precipitation and through the magnetopause. And we're defining magnetopause loss as when the electron moves onto a field line that changes its topology to go from a closed field line where both the points map into the ionosphere itself to an open field line where one of those field lines is now open to the ISM, and that particle is quickly lost out the back of the domain of the simulation. So we're doing accurate test magnetic field tracing throughout the simulation itself to know exactly what the magnetic field topology is of the magnetic field line that the electron is moving on. And similarly, we determine the particle is precipitated when it reaches the inner boundary of our simulation, which is 1.05 RE in the simulation. So we put it just above the ionosphere, and we assume a magnetic dipole between the MHD inner boundary at 1.5 RE down to the ionosphere altitude. So particles that don't bounce before the ionosphere are considered lost to the system. And that's how we quantify it here. What you're seeing in the right-hand side is an evolution of those loss processes as a fraction of the total existing belt itself. And here you can see that the majority of the loss is dominated through the magnetopause, accounting for removing 40% of the initial radiation belt. However, pitch angle scattering also causes a significant fraction of loss, accounting for a third of the total loss of 20%. And pitch angle scattering also accounts for or increases loss by 14% when compared to the run where no wave particle corrections were included. And in that run, there was zero precipitation loss, only loss through the magnetic deposit itself. So again, a significant source of loss throughout the main phase of the storm. And on top of looking at just kind of total loss fraction, we can also produce synthetic precipitation maps of the precipitating electron fluxes. So what I'm showing here on the right-hand side is the precipitation accrued over the entire simulation. So this is over a 14-hour period. And this also incorporates loss in both northern and southern hemisphere combined into one single plot. And I'm showing the precipitating number flux on the left-hand side, the mean energy of that precipitating flux in the middle panel, and the energy flux on the right-hand side. And the first thing you can see is that if you look at the middle panel, that the majority of the particle precipitation in terms of number flux is occurring in the pre-midnight to dawn sector, exactly where the coarse waves are largest. And this precipitation has a mean energy around 100 keV or so in our simulation. However, as you notice in the top right-hand panel is that the erosion of the plasmasphere causes a lower density region that shifts the resonance to higher energy particles close to the plasma spots, so at lower L shells on the day side itself. So if you look at the mean energy as we progress, that would map to in the ionosphere to these lower L shell regions, so lower latitudes here on the day side, where we can see the mean energy starts to increase and create an energy dependence of our precipitation that matches, it seems to match the plasma, the evolution of the cold plasma in the MHD simulation, which results in more efficient scattering of those particles. So this is extremely powerful tool that we can now connect precipitation features directly to how the plasma varies in our global MHD simulation, as well as to the wave amplitudes that are driving that precipitation themselves. And trying to do that in a self-consistent way is important, as I've hopefully shown. And before ending, I just wanted to show another really neat application of this simulation. And I won't go too much because I know we're getting close to our time. I'll leave some time for questions. While in the previous study, we were looking primarily at the evolution of the pre-existing belt and didn't include variations due to injections. Injections can be caused by these mesoscale flows, which carry dipolarizing flux inwards into the inner magnetosphere. And these flows are characterized both in observations from GOES, which is work done in 2004 by Shinotani, where he used GOES measurements of these mesoscale flows to provide a superposed epoch analysis of them, which is down here in the bottom left panel in the data. And what was done by Mike Wilberger in 2015 was taking an LFM simulation, doing a similar superposed epoch analysis of those mesoscale flows to show that both in the data and in the model, we see these mesoscale flows that show an increase in the BZ component of the magnetic field, which is shown here in the middle panel, and a corresponding decrease in the plasma density in these mesoscale flow channels. And again, this increase in magnetic field and decrease in plasma density are both conditions that shift our resonance region up to much higher energy particles, similar to how that density depletion region did that we saw due to the erosion of the plasmasphere. So quick notes here that we can show kind of just exactly how those mesoscale flows can affect the actual pitch angle scattering of these particles. What I'm showing here on the right-hand side are two time periods, which are only 4 minutes apart. The background field is showing the residual magnetic field, which is the magnetic field with the dipole component removed. So that black corresponds to regions where the magnetic field is depressed, and red corresponds to regions where the magnetic field is compressed itself. And in the second, and then this color contour on top is showing the bounce average diffusion coefficients, again, that we showed before, overlaid directly on top. And these top two panels are showing, again, a 2 MeV electron with an equatorial pitch angle of about 75 degrees. And these bottom panels are lower energy electrons of 30 keV with an equatorial pitch angle of 15, so much closer to the lost cone of these cell shells. And in the second panel, you can see an incursion of these mesoscale flows, which bring dipolarizing flux inwards. And that as these particles come, as these mesoscale flows come in contact with the coarse waves in our simulation, you can see that at least for 2 MeV particles, it's just shifting the resonant region up, where now it's allowing very energetic MeV electrons to resonate where they otherwise would not be. And in addition, for these lower energy particles, this change in background plasma conditions has now increased the bound's average diffusion coefficient such that the diffusion coefficient is now in the order of minutes, just like the propagation time of these BBS through these periods. And so that potentially can drive very rapid scattering events, as we know. These mesoscale flows can also drive coarse waves behind them. So I will wrap up there because I know we're getting close to 4. So just for our conclusions, we have implemented wave-particle interactions into our global MHD and test particle simulation. This is done by solving the Fokker-Planck diffusion equation as a stochastic differential equation, which is based off quasi-linear diffusion coefficients that are directly informed by the time-varying magnetic field and density from the MHD simulation. And this evolution of the background magnetic field and density strongly impact both the location and energy dependence of resonating particles, which directly correspond to the acceleration of the particles and also due to the precipitation. And this is a really powerful tool that we can then now use to try and directly tie precipitation features and acceleration features due to wave-particle interactions back to the actual plasma conditions that are driving those changes. So thank you very much, and I can take any questions.
Thank you very much. Is there any question first in person, maybe?
Anyone online?
Yes.
There's one.
There's one.
I could choose a question. I didn't check. No, I don't. But in terms of computation, like how heavy is this simulation? Because like when you try to couple particle with MHD and stuff like that, and it can do pretty well. Like, do you have any numbers, so that we can have an idea of how heavy this computation is?
Yeah, so it is very heavy computationally. The actual MHD simulation you can run it's not heavy itself, but when we include it takes about several 24-hour period running on about 1,000 cores to run the MHD simulation for 15 hours. The test particle simulations, at least are significantly less than that. However, the wave-particle interactions initially increases the computation of the test particle simulations by a factor of 3. And then on top of that, you're accelerating these particles to much higher energies, which reduces each individual time step. So it's a much larger effect in terms of increasing the actual computational cost of those simulations. So as you're including more and more MeV particles in your simulation, it just goes exponentially slower throughout. So again, at the moment, we are running 2 million test particles through these simulations. I guess feasibly, doing a 14-hour period is probably, at least at the moment where we're capping out for these test particle simulations. It's been very, very long storm time periods. Is a little bit challenging at the moment, but we're working on making that much more efficient in the process so we can measure much more longer periods.
Thank you.
When the distribution of particles are used like normal distribution to, but as the initial conditions, or you use different kind of distribution for those particles?
Yeah, so we, at least when we're initializing them, we initialize them uniformly in energy, L shell and pitch angle and MLT. However, the real effect of the distribution comes in when we're weighting it and how we choose to weight the particles to actually relate that to a physical distribution function. And we can, there's a bunch of different techniques that we can use to do that. You can weight them based off the actual MHD temperature and density maximum distributions you have at the particle's location. But in this study, since we have Van Allen probes measurements during this event, we actually use Van Allen probes phase-space density measures to weight the test particle initially, and then evolve those distribution functions as a function of weight.
Right, thanks.
So how well do you end up resolving the ring current?
The ring current,
Yeah.
there is a paper being published by Anthony Sciola, which is should be accepted soon, where he's done for this exact 2013 St. Patrick's Day event, has looked at he's used a detailed RCM analysis of RCM compared to the ring current from the Van Allen probes, and does actually shows the energy dependence of the ring current as a function of time, and it gets very good agreement with the measurements themselves. So that should hopefully be published very soon, and I will point you to reading that paper for more in-depth discussion.
And sorry, and remind me, when your waves, are those generated by the particles, or are those just imposed in the system?
Yeah, so for the Whistler waves, we are ingesting them from an empirical wave model that we are getting, that are derived from Van Allen probes measurement over the lifetime of the mission. They're not inherent in our MHD simulation, so we're taking that from an empirical model, but we're trying to ingest them in a consistent way in the simulation. So we're reparameterizing it by distance from the plasma plus, so that we're not, if we just included it by L shell, we would then, as the plasma plus kind of extends to larger L shells, we might have coarse waves, but we wouldn't necessarily expect them. So that's one way we were trying to at least be consistent between ingesting the empirical Whistler mode coarse wave amplitudes into the global simulation.
Thank you.
Any other question?
Did we ask the question that's online?
Yeah.
No, it's a link to the preprints.
Okay.
that
Oh,
just-
great.
Okay.
Right. And any other question? Let's think if they're speaking again. Thank you so much.